dynamic equilibrium. So dynamic means when we look at a system, it looks like nothing's going on, but all changes are occurring, but it's at equilibrium. And I like to think about equilibrium as a teeter-totter. So one of your first jobs is that if a system is described as being at equilibrium, I want you to have these 4 points memorized. That equilibrium is only truly achieved in a closed system, nothing in, nothing out. The rate of the forward process is equal to the rate of the reverse process. Concentrations are constant. And if it's a solution-based equilibrium, the solution is saturated. Okay, couple of like little graphs here. So concentration. We have a reaction. Reactant A's make product B's. So if we have a closed system, like think about a capped water bottle, and we only put in A molecules. So here we go. We are starting off, this represents the concentration of A. A is the only thing in there. Since we did not put any of the product B's in there, product B's concentration would start here, 0. No concentration present. But if we let that closed system set and we leave it undisturbed, reactant A's will start to make some of B. So what happens as reactant A's start to react, we see a decrease in their concentrations because they are being converted chemically into B. So all of a sudden we start to see the concentration of B starting to be present. So some of A starts to disappear because it's being used to make B, and now we start to see B appear. And if we reach equilibrium, it gets to a point where both A and B's concentrations stop changing. So take a look here. So when we reach this type of point on a graph, we've reached a point of equilibrium where A's concentration is no longer increasing or decreasing. Same thing with B, its concentration is no longer increasing or decreasing. The concentrations are constant. So I like to call this con-con. And notice, A's concentration is not the same as B's. They're not equal concentrations. It's just both concentrations are no longer changing. Neither are increasing or decreasing. So we have con-con, constant concentrations. Well, while this is happening, we have the rate. So if you have the word rate, you might want to add rate. We're talking about the speed, how quickly the reactions are occurring. Well, if we only have A in the system, okay, the rate of the forward reaction is going to be really high because you only have rates of, or only molecules of the reactants, only molecules of A, and they are having all kinds of collisions. Because there are no B molecules in there, the reverse reaction is not happening at this point. So its speed is 0. So I'm going to say this is the forward. So forward means A is making B, and the reverse reaction is where B is reforming A. So since we only have A in the system, all the A molecules are finding each other, having collisions, and reacting to forming B. So as the reaction starts, the forward reaction will start to slow down, right? Because some of the A's are consumed, and now we start seeing B molecules being present. So now the B molecules can start to collide and start to reform the A's. So we get to a point in this process where the two reactions their rates are the same. and that's where we have reached a point of equilibrium, because the rate of A making B equals the rate of B making A. So when we reach this point where the forward process rate equals the reverse reaction process rate, I like to say that we are at a point of requal. So when we're talking about the rates, requal, and when we're talking about the concentrations, con-con. So when we reach con-con and requal, our system is described as being at equilibrium.